I want you to just imagine for a second the absolute worst possible time for an online shopping cart to fail.
Oh, man.
Right. Like, I don't mean a random Tuesday afternoon. I'm talking Black Friday or, you know, the final hour of some heavily advertised holiday sale.
Yeah, the highest stakes possible.
Exactly. You've spent like an hour clicking around, carefully curating this massive list of gifts.
Yeah.
You've stacked the deals, applied all the promo codes, and you are fully prepared to just give this company your money.
You're at the finish line.
Yes, you click add to cart for that final crucial item, but instead of that satisfying little notification, you get the spinning wheel of death
The worst.
and then a fatal error message. And you have to wonder why. What if the act of clicking that button gave you an error simply because, I don't know, a single server in the data center 1,000 miles away just happened to restart at that exact millisecond?
I mean, that is basically the ultimate nightmare scenario for any massive e-commerce operation.
It really is.
Because that error message, it's not just a lost sale in one isolated moment. It's a fundamental breach of trust.
Yeah, a customer experiences that friction, and they are incredibly likely to just open a new tab, go to a competitor, and they might never come back.
Exactly.
Which perfectly brings us to the source material for today's deep dive. We are unpacking a genuinely seminal document in the world of computer science and systems architecture.
It's a big one.
It's a 2007 paper from Amazon titled Dynamo, Amazon's highly available key value store. And this paper, it essentially serves as the blueprint for modern cloud computing and, like, the entire NoSQL movement.
Yeah. Reading this paper today, it feels like you're looking at the actual foundation of the modern internet.
Right.
It fundamentally shifted how the whole software engineering industry thought about storing data at, a massive distributed scale.
So our goal today, the mission for this deep dive, is to examine exactly why Amazon made this incredibly radical decision. They intentionally sacrificed data consistency.
Which is huge.
Right, the idea that every part of a system has to perfectly agree on the data at all times. They sacrifice that to guarantee absolute unbreakable availability. We want to understand how they built a system that just flat out refuses to reject your attempt to write data.
It's fascinating.
Okay, let's unpack this. Before we look at the actual architecture of Dynamo, we really need to ground ourselves in the sheer scale of the problem Amazon was dealing with back in the mid-2000s.
Yeah, you have to have that context.
Because they were migrating away from monolithic applications, where everything runs in one giant code base, and moving toward a highly decentralized, loosely coupled architecture.
Right, a service-oriented architecture. And the scale is it's the necessary context for literally everything that follows in this paper.
So how big are we talking?
Well, consider the operational math of Amazon's infrastructure during that time. They were orchestrating tens of thousands of servers, running hundreds of different services just to load one single web page on Amazon, to render the product catalog, the recommendation engine, the pricing service, the reviews.
All the stuff we take for granted on the page.
Exactly. That one page load might require calls to over 150 different services under the hood before the HTML even gets sent to your browser.
Okay, and we know that traditionally, all the data for those services was stored in relational databases. We're talking standard SQL databases built on those classic ACID properties.
Right. Atomicity, consistency, isolation, durability.
Right. And for a bank, you absolutely want ACID. You want the system to lock the ledger, guarantee the money left account A and entered account B, and make sure nobody else can read that row of data until everything is perfectly consistent.
You need that certainty.
I assume a lot of folks listening are super familiar with traditional SQL environments, but locking an entire row or table for a transaction, that doesn't scale well when you have 150 different services trying to render a page simultaneously, right?
No, it doesn't at all. The locking mechanism itself becomes the bottleneck.
Right.
When you demand strong consistency across a distributed relational database, the database essentially has to declare a freeze.
Right.
It forces all concurrent processes to just sit there and wait.
So in an architecture where a single user request cascades into 150 downstream requests, waiting is just catastrophic.
It really is.
It's kind of like a 150-person relay race. The baton has to be passed flawlessly 150 times just to load the web page before the customer gets bored and leaves.
That's a great way to think about it.
If even one runner in that race, like a traditional database, suddenly pauses, holding the baton just to carefully tie their shoe and ensure perfect consistency before taking another step, the entire race stalls out.
And Amazon didn't just have this vague internal goal to be fast. They had incredibly strict service level agreements, or SLAs, that governed all these internal services.
Right. The engineering teams basically had hard contracts with each other.
Exactly. And the most fascinating part of the Dynamo paper, at least early on, is how they measured those SLAs. They explicitly rejected looking at average or median response times.
Yeah, the paper points out they demanded 300 millisecond response times at the 99.9th percentile, and that was for a peak load of 500 requests per second.
Which is just a profound philosophical shift in performance engineering.
How so?
Well, when you monitor an application, the average latency completely masks the worst experiences.
Oh, right, because a bunch of fast load times hide the slow ones.
Exactly. And in e-commerce, those worst experiences disproportionately affect your most valuable customers.
Okay, wait, I have to pause on that because that sounds completely counterintuitive. Why would the most valuable customers have the worst performance?
It comes down to their data profile. Think about a brand new user.
Okay.
They have almost no history. The database can retrieve their empty profile in a fraction of a millisecond.
Right, there's nothing to load.
But a power user, someone who has purchased thousands of items over 10 years, who has massive, highly personalized review histories and complex recommendation graphs, their data footprint is absolutely enormous.
Oh, wow. Yeah.
It simply takes the database longer to query and process their profile. So, if you engineer your systems to just optimize for the average user, you are systemically punishing your most loyal, highest spending demographic.
They get the slowest page loads just because they've bought so much stuff.
Exactly.
Think about your own work environment for a moment. Are you measuring the success of a process by how it runs on an average day? Or are you measuring it by how it holds up during the worst 0.1% of edge cases? Amazon basically realized that building for the average would inevitably throttle their heavy hitters.
And this realization, it basically forced them to reconsider relational databases entirely.
Because they just couldn't keep up.
Right. The hardware and the specialized personnel required to maintain those ACT guarantees at petabyte scale, they were becoming prohibitively expensive. But more critically, relational databases inherently fail closed when network disruptions occur.
Fail closed, meaning they just shut down.
Right. In a network of tens of thousands of servers, components fail literally every single minute. Routers drop packets. Hard drives corrupt. And when a network partition occurs, a traditional database will prioritize consistency over availability.
It'll just lock up.
Yes. It will refuse to answer queries rather than risk serving stale data.
Which means the shopping cart fails. And that exposes the core tension of the entire paper. Because relational databases were stalling out at that 99.9th percentile during routine hardware failures, Amazon had to completely reinvent their storage layer.
They had no choice.
They had to abandon perfect consistency to create this always writable data store.
Yeah, and we are touching on the CAP theorem here, which is a fundamental principle of distributed systems formulated by Eric Brewer.
Right.
It states that in a distributed data store, you can only provide 2 of 3 guarantees: consistency, availability, and partition tolerance.
Though, I mean, in a wide area network, partition tolerance isn't really a choice, right? Networks will split, cables will be cut.
Exactly. So you are really forced to choose between consistency and availability.
And Amazon chose availability. Loudly and clearly. The mandate for Dynamo was that no update, no write operation should ever be rejected.
They called it the shopping cart imperative.
Right. Customers must always be able to add or remove items from their cart, even if network routes are flapping or entire data centers are offline. The cart must remain open for business.
And to do that, it requires a massive shift to optimistic replication and eventual consistency.
Eventual consistency, meaning it'll get sorted out eventually.
Right. You accept the right operation immediately on whatever local node the user happens to connect to, trusting that you can sync that data up with the rest of the cluster in the background, eventually.
See, this is where I struggle with the practical application. A database that fundamentally does not guarantee it has the correct answer seems incredibly dangerous.
It sounds chaotic.
Yeah, like if I add a $2,000 television to my cart and the system accepts that right on a severed node, what happens when I try to check out? How do you run a multi-billion-dollar platform on an infrastructure that explicitly admits it might not actually know what's in your cart at any given second?
Well, it comes down to prioritizing the business funnel over mathematical purity.
Okay, explain that.
Rejecting a customer's attempt to add an item to the cart is a quantifiable immediate loss of revenue. It is a fatal error in the user journey.
They just leave.
Exactly. Conversely, accepting the item and risking a temporary inconsistency is a recoverable state. Dynamo basically flips the traditional database model on its head.
How so?
Traditional databases keep read operations simple by shifting all the complexity and failure risk onto the write operation. They block the write until a consensus is reached. Dynamo, on the other hand, pushes all the complexity of conflict resolution onto the read phase.
So the system basically says, I'll take your data now, no questions asked, but whoever tries to read this data later is going to have to do the heavy lifting of figuring out if it's accurate.
Precisely. The business logic dictates that keeping the top of the funnel open is vastly more valuable than ensuring back-end harmony in that exact millisecond.
But to achieve this always writable state across tens of thousands of servers without a central bottleneck, they needed a radical approach to data partitioning, didn't they?
Yeah, they had to decentralize everything.
Which brings us to the architecture of decentralization.
Yeah.
Because if we are accepting writes everywhere simultaneously, how do we organize which servers hold which pieces of this massive data set?
Right.
The system relies on a principle of symmetry, meaning every node in Dynamo has the exact same set of responsibilities. There are no master nodes delegating tasks.
Because centralized coordination introduces a single point of failure. If your master node dies, the whole system goes down.
Exactly.
So to partition data without a central directory, Dynamo implements something called consistent hashing.
Okay, let's define the mechanics of that. Standard hashing is pretty common, right? You take a piece of data, run it through an algorithm, and get a unique identifier.
Right.
If you have 10 servers, you might take that identifier, use a modulo operator against the number 10, and assign it to a server.
Which works fine until you scale.
Yeah, because if you add an 11th server, the modulo math changes for every single piece of data. You'd be forced to move almost your entire database to new servers just to rebalance.
Which is a nightmare. Standard modulo hashing is extremely brittle for that exact reason.
So how does consistent hashing fix it?
Consistent hashing solves the rehashing problem by treating the output range of a hash function. And Dynamo uses MD5 as a fixed circular space, or a ring.
A ring?
Yeah, the MD5 algorithm generates a massive 128-bit integer space.
Yeah.
Imagine taking that massive range of numbers and just wrapping it around into a circle.
Okay, let's use an analogy here. I like to imagine consistent hashing like a giant roulette wheel.
Oh, that works.
The outer edge of the wheel is the 128-bit hash ring. Now, we take our physical servers and run their IP addresses through that same hash function, which assigns them a specific random number on that ring.
Right.
It's kind of like dropping a bucket onto the edge of the roulette wheel at a specific position.
So now when a customer generates data, say a shopping cart key, the system hashes that key to find its position on the ring.
And it lands on a specific number on the rim.
Exactly. To find out which server is responsible for storing it, the algorithm just walks clockwise around the ring from that number until it encounters the very first server position.
So the little silver marble of data lands on the rim, and it just rolls clockwise along the edge until it plinks into the very first bucket it hits.
That's a perfect visual.
And the beauty of this is what happens when you add or remove a server. If a bucket catches fire and disappears, the marbles simply roll past its old spot and drop into the next bucket clockwise.
Yes, you only affect the immediate neighbor rather than reshuffling the entire roulette wheel.
But the paper identifies a pretty significant flaw with this basic implementation, right?
Yeah, they ran into a big issue. If you assign nodes randomly onto this ring, the distribution of data is almost never uniform.
Because random isn't evenly spaced.
Exactly. You end up with large gaps between some nodes and tiny gaps between others. A node with a massive empty space behind it on the ring is going to catch a huge disproportionate amount of traffic.
Plus, treating every server as one single bucket ignores hardware realities entirely.
Right.
The roulette wheel doesn't know if a bucket represents a state-of-the-art supercomputer or like a 10-year-old desktop machine. It treats them equally.
Which is inefficient. So Amazon solved this by introducing virtual nodes, or tokens.
Okay, tokens.
Instead of mapping one physical server to one single position on the ring, a physical server is assigned multiple tokens. It represents multiple virtual nodes scattered randomly all around the hash space.
So a powerful new server doesn't just put one bucket on the wheel. It claims, say, 200 virtual buckets and scatters them everywhere.
Right.
While a weak, older server might only get 20 virtual buckets.
And by scattering these virtual nodes, the load naturally balances itself. The probability of any one physical server getting overloaded drops to near zero because its jurisdiction is cut up into hundreds of tiny, evenly distributed slices.
That's so smart.
And when a node is added to the cluster, it claims virtual positions, effectively siphoning a perfectly proportionate amount of load away from its neighbors. And it does this without requiring any manual data rebalancing.
It's brilliant. So we have this beautifully decentralized ring, but we haven't actually solved the chaos of the CIP theorem.
No, we haven't.
Because if writes are always accepted everywhere, we inevitably encounter the problem of version branching. We really need to talk about vector clocks and how data travels through time in this system.
Yeah, this is where it gets complicated.
What actually happens when a network split occurs and two different servers record conflicting updates to the exact same shopping cart?
This is the messy reality of eventual consistency. Imagine the connection between a data center on the East Coast and one on the West Coast is totally severed.
Okay, fiber cable gets cut.
Right. A customer's mobile app might be interacting with the East Coast servers, adding a book to their cart. But simultaneously, a background automated process might be trying to update that exact same cart on the West Coast servers.
And because of the mandate, the system accepts both rights.
Exactly. We now have two conflicting parallel realities of the same object.
So how does Dynamo fix it? They use vector clocks, right? To track the causality of these universes so it can stitch them back together later.
Yes. A vector clock is basically a data structure. It's a list of pairs attached to every version of a data item.
Okay, what's in the pair?
The pair consists of the node that handled the write and a counter that increments every time that specific node modifies the object.
Let's trace the life cycle of a piece of data to see this in action because it's kind of abstract. We'll call the data object D. So a client requests to write object D. The load balancer routes this to server X. Server X writes it and attaches a vector clock. We now have version D1, and its clock reads server X counter 1.
Easy enough.
The client then modifies the object again, and server X handles it again. We get version D2, and its clock reads server X counter 2.
Okay, and at this point, if the system reads both D1 and D2, it performs what they call syntactic reconciliation.
Meaning it uses the math.
Right, because the clock for D2 mathematically descends from D1, meaning every counter in D1 clock is less than or equal to the counters in D2's clock. The system knows with absolute certainty that D2 is the authoritative newer version.
So it just deletes D1.
Exactly. Syntactic reconciliation is easy.
But then the meteor hits the fiber optic cable, the network splits, the client tries to update the object again, but server X is unreachable.
Right.
So server Y steps up to keep the system highly available. Server Y handles the write, creating version D3. Its vector clock now reads server X to server Y1.
Concurrently, a different client or process updates the cart, but it hits server Z on the other side of the split.
Okay.
Server Z creates version D4. Its vector clock reads server X2, server Z1.
So we have our parallel realities. D3 and D4 exist simultaneously, and if a node later looks at D3 and D4, syntactic reconciliation completely fails.
That's because D3's clock doesn't contain Z's update, and D4's clock doesn't contain Y's update.
Right. They are causally divorced. The database layer has literally no mathematical way to know which version is the correct final state.
Now, traditional databases might default to a blunt last write wins, based on a timestamp.
Just pick the newest one.
Right. But timestamp resolution in distributed systems is notoriously unreliable due to clock drift. Servers rarely have the exact same time.
So Dynamo refuses to guess.
Exactly. When syntactic reconciliation fails, Dynamo triggers semantic reconciliation. It hands both versions of the data back up the stack to the client application.
So the database basically throws its hands up and says, look, I just store bytes. I don't know what a shopping cart is. You figure it out.
That is exactly what happens. The shopping cart application has the business logic. It receives D3 and D4, recognizes that one cart contains a book and the other contains a television, and it executes a merge function to combine them into a single cart containing both items.
Which perfectly fulfills the mandate. An add to cart operation is never lost.
Yes.
Though I do wonder about the edge cases. The paper mentions that while additions are preserved, deletions can occasionally resurface.
Yeah, that is a known artifact of semantic reconciliation.
How does that happen?
Well, if you deleted a pair of headphones in branch D3, but branch D4 didn't register that deletion because of the network split, the merging logic might conservatively choose to keep the headphones in the cart.
Just to be safe.
Right, to avoid accidentally dropping an item a user actually wanted. The business calculation is that forcing a user to manually remove an item a second time is far less damaging than secretly losing an item they intended to buy.
That makes total business sense. But I'm curious about the vector clocks themselves getting unwieldy.
Oh, the metadata bloat.
Yeah. If an object is updated hundreds of times across dozens of different servers during rolling network outages, that list of node and counter pairs is going to seriously bloat the metadata of the object.
It would, yeah. So Dynamo implements vector clock truncation to handle that bloat.
Okay, truncation.
If the list of pairs exceeds a predefined threshold, Amazon usually set it around 10 pairs. It just chops off the oldest pair.
Wait, if you truncate the oldest timestamp, don't you lose the causal history required for the syntactic reconciliation we talked about?
You do.
You could end up flagging two direct ancestors as parallel conflicts just because they forgot their shared history.
You absolutely risk artificial conflicts, yes. The system might ask the application to merge two objects that actually could have been resolved mathematically if the full clock history was intact.
That seems risky.
But Amazon's engineering team noted in production that they never actually saw this issue materialize.
Really? Never.
Yeah. The truncation threshold of 10 was deep enough to capture almost all real-world partition events without triggering those artificial semantic merges.
Okay, so we've established how data maps to the ring and how vector clocks track parallel histories. But we need to look at the physical mechanics of a read or write operation when servers are actively failing.
Right, the real-world execution.
How does a node guarantee data replication in such a chaotic environment?
Dynamo uses a quorum-like technique, and it's governed by three configurable variables, N, R, and W.
Okay, N, R, and W. Break those down for me.
N is the total number of replicas. It's how many distinct servers should store a copy of the object.
Okay.
R is the minimum number of nodes that must respond for a read operation to be considered successful. And W is the minimum number of nodes that must acknowledge a write operation for it to succeed.
So the standard configuration Amazon used was 3, 2, 2. Data is written to 3 servers. You need 2 to agree on a read and 2 to confirm a write.
Exactly. And if R plus W is greater than N, you have what's called a strict quorum.
Which guarantees that at least one node in your read group will have the latest write.
Right. However, a strict quorum directly violates Dynamo's primary directive of ultimate availability.
Wait, why?
Because in a strict system, if data is mapped to nodes A, B, and C on the ring, you must hear from a majority of those specific 3 nodes. If A and B are offline due to a rack failure, your write operation fails.
But we established that Dynamo refuses to fail the write. Ever.
Right, so to bypass this, Dynamo employs a sloppy quorum.
Sloppy quorum. I love that name.
It's very descriptive. Instead of demanding a response from the specific preferred nodes, A, B, and C, the system simply takes the first N healthy nodes it finds as it walks clockwise around the hash ring.
Okay, let me make sure I have this. So if a user tries to write a part to node A, but A and B are completely unresponsive, the system doesn't throw an error.
No error.
It just keeps walking the ring, it walks past C and finds node D and node E, which are perfectly healthy, and it hands the data to them instead.
Exactly. No D and E accept the data, but they recognize it doesn't actually belong to them based on the hash map.
Right, they know they're just holding it.
So they utilize a mechanism called hinted handoff. Node D stores the replica in a separate local database and attaches a piece of metadata, a hint stating, this data is ultimately bound for node A.
Here's where it gets really interesting. It operates just like a delivery driver finding a blocked road.
Oh, that's a good analogy.
Yeah, if I order a package to my house at node A, but the road is out, the driver doesn't return the package to the warehouse. They drop it off at my neighbor's house, node D, with a sticky note saying, hold this for A and run it over as soon as the road clears.
And node D will periodically scan its hinted handoff database. The moment it detects via the gossip protocol, so we'll get to that node A is back online, it transmits the replica to A and then safely deletes its own temporary copy to free up space.
That is so elegant. The sloppy quorum combined with hinted handoff is what makes that 99.9th percentile SLA possible.
The secret sauce.
Even if an entire data center loses power, taking out nodes A, B, and C simultaneously, the write operation simply slides further down the ring to a different data center, drops off the hinted handoffs, and returns a success message to the customer.
The front-end user experience is completely insulated from the back-end hardware catastrophe.
But there is a mathematical vulnerability to hinted handoff, though, right?
There is. It relies on the assumption that failures are transient.
Transient meaning temporary.
Right. If node D, the neighbor holding the package, suffers a catastrophic disk failure before node A comes back online, the hinted replica is permanently lost.
The sticky note burns up in a fire.
Exactly. The
Right.
system now has replicas scattered around the ring that are out of sync, and it has lost the hints that would normally trigger that self-healing process.
So how do they fix permanent failures?
To combat permanent failures and silently corrupted data, Dynamo implements a background anti-entropy protocol.
Entropy being the natural degradation of order in a system.
Yes. So anti-entropy is the mechanism to constantly compare replicas and push them toward consistency.
But wait, comparing massive databases across a network is computationally expensive. If two nodes hold 1 million shopping carts each, they can't just send their gigabyte-sized databases over the wire to look for discrepancies.
No, it would saturate the network bandwidth instantly. The whole system would crawl to a halt.
So how do they compare them?
Amazon utilized Merkle trees to solve the comparison problem cryptographically.
Okay, Merkle trees. Let's break that down.
A Merkle tree is basically an upside-down hash tree. At the very bottom, you have the leaves of the tree. Each leaf is a cryptographic hash of a single individual key-value pair, like one shopping cart.
Right.
Then you group a set of those leaves together, hash them, and that creates a parent branch.
And you just keep doing that.
Yeah, you continue grouping and hashing those branches as you move up the tree until you reach the very top, culminating in a single root hash.
So that root hash is basically a cryptographic fingerprint representing the entire massive data set.
Exactly. And the magic is, if you change even a single bit of data in one shopping cart at the leaf level,
It changes that leaf's hash.
right, which changes the parent branch's hash, which cascades all the way up and radically alters the root hash. It's the avalanche effect of cryptographic hashing.
This allows for incredibly efficient synchronization.
Very efficient.
Because Node 1 and Node 2 don't exchange entire databases, they simply exchange their root hashes. Just a single string of text.
Yes. If the root hashes match, they have 100% mathematical certainty that their databases are perfectly identical. The transaction takes milliseconds and requires almost zero bandwidth.
But if they don't match,
If the root hashes do not match, the system traverses down the tree. They exchange the hashes of the branches directly below the root, they ignore the branches that match, and only pursue the branches that differ.
following the breadcrumbs of the mismatch.
Exactly. They continue this targeted descent, narrowing down the mismatched branches until they pinpoint the exact leaf, the specific shopping cart that is out of sync.
And then they only transmit that single piece of data across the network to resolve the inconsistency.
Right. It's basically a binary search for corruption.
It's so cool. If you've ever used a massive cloud storage platform and you edit a single text file inside a folder containing terabytes of video, the cloud syncs it almost instantaneously without re-uploading the whole folder.
Yes. That is Merkle tree logic operating in the background. It isolates the delta with extreme precision.
But for these background synchronization processes to work, every node needs to know the topology of the ring. They need to know who is alive, who is dead, and who owns which virtual tokens.
Because there's no central boss to ask.
Right. So without a central master directory, Dynamo utilizes a decentralized gossip-based membership protocol.
And the term gossip protocol perfectly describes the mechanism. It's essentially epidemic broadcasting.
Epidemic like a virus.
Yes. Every node in the Dynamo cluster randomly selects one of its peers and initiates a handshake.
Just a random check-in.
Exactly. They exchange their current view of the ring, who they think is online, and the token assignments. They reconcile their views, update their internal maps, and then the very next second, they gossip with someone else.
It's an O log n propagation spread. Because it's exponential, even in a cluster of thousands of servers, a rumor about a new node joining or a node failing will infect the entire network in a matter of seconds.
And the true beauty of epidemic protocols is their resilience.
How so?
Well, if a network partition occurs, the nodes on one side gossip with each other and agree that the other side is dead.
Because they can't reach them.
Right. But when the partition heals, it only takes one successful gossip handshake across the divide for the two halves to instantaneously reconcile their maps and realize everyone is actually alive.
Wow. We have spent a significant amount of time detailing the theoretical architecture here. Consistent hashing, vector clocks, sloppy quorums, Merkle trees, gossip protocols.
It's a lot.
It is an incredibly elegant design. But the true value of the Dynamo paper lies in what happened when Amazon deployed this architecture into production.
Theory rarely survives contact with the enemy.
Exactly. And in this case, the enemy was the holiday traffic of the world's largest store.
The production lessons are honestly the most compelling part of the document.
Because the engineering teams immediately had to start making practical trade-offs, right?
Yeah. The first major hurdle was the friction between performance and durability.
Meaning keeping data safe versus doing it quickly.
Right. Even with the decentralized architecture, guaranteeing a 300 millisecond response time at the 99.9th percentile was difficult when they were constrained by the physics of spinning hard drives.
Right, because writing data to a disk requires a physical platter to spin and a magnetic head to align. It takes a few milliseconds.
And under heavy concurrent load, those milliseconds stack up. They create latency spikes that violate the SLA.
So how did they bypass the disk bottleneck?
Amazon implemented an in-memory object buffer. When a write request reached the coordinator node, instead of blocking the request until the data was safely written to the physical disk, the node simply stored the data in its main memory, its RAM, and immediately returned a success message to the client.
Just skip the disk entirely?
Initially, yes. A background thread would asynchronously flush the buffer to the disk a few milliseconds later.
The danger there is pretty obvious. RAM is volatile memory.
Very volatile.
If the server loses power or the software crashes in the brief window before the background thread flushes to disk, that data is permanently vaporized.
It's gone.
They intentionally compromised absolute durability for speed.
They absolutely did, but they quantified the risk against the reward. The paper actually features a graph demonstrating that this in-memory buffering optimization lowered the 99.9th percentile latency by a factor of 5.
A factor of 5.
It completely smoothed out the latency spikes that were causing SLA violations. So, for certain high-velocity services, the immense performance gain was deemed worth the microscopic risk of data lost during a catastrophic server failure.
Wow. The paper also details a significant evolution in how they handled partitioning, like how they actually laid out the hash string. They went through 3 distinct strategies because their initial theoretical model failed in production.
Yeah, let's look at strategy 1.
Okay.
Initially, they assigned T random tokens to every physical node. It distributed the load evenly, as we discussed earlier, but it created an operational nightmare when adding or removing nodes.
Ah, the bootstrapping problem.
Exactly.
If a new node joins the ring, it claims random tokens, which means it has to take over random key ranges from existing nodes.
Right.
But because the ranges are completely random and arbitrary, the existing nodes have to scan their entire massive databases to locate the specific keys to hand over.
And executing a full table scan on a database while it is actively serving production traffic that causes massive performance degradation.
It slows everything down.
The paper notes that during high traffic periods, bootstrapping a single new node using strategy 1 could take an entire day.
A whole day just to add one server.
Yes. It severely hampered their ability to scale elastically during traffic spikes.
Which totally defeats the purpose of the architecture. So they iterated. Strategy 2 attempted to fix this by keeping the random tokens but making the partitions equal size.
Which was better but not perfect.
But they ultimately landed on strategy 3, which fundamentally changed the geometry of the ring.
Right. In strategy 3, they stopped dealing with random token ranges entirely.
What do they do instead?
They divided the entire 128-bit hash space into Q equally sized fixed partitions. They then decoupled these partitions from the physical nodes.
Decoupled them.
Yeah. A physical node is no longer assigned random points on a ring. It is simply assigned a certain number of these predefined fixed partitions.
And the key advantage here is how the data is stored on disk, right? Because a partition is a fixed known entity, a node can store each partition in a distinct separate file on the hard drive.
Exactly. When a new node joins and needs to take over a partition, the existing node doesn't have to scan its database at all.
Oh, that's huge.
It simply locates the physical file corresponding to that partition and transmits it as a contiguous block of data.
It transformed bootstrapping from an intensive database query into just a simple file transfer.
It reduced the metadata each node had to manage by several orders of magnitude.
Just by changing the administrative boundaries of the data, they solved the scaling bottleneck. That's incredible. But of all the operational data shared in this paper, there is one statistic that I find absolutely fascinating.
I think I know which one you're talking about.
We've spent this entire deep dive discussing the complexities of vector clocks, semantic reconciliation, and the chaos of parallel realities caused by eventual consistency. But the paper actually quantifies how often version conflicts happen in the real world.
The metric is genuinely staggering.
Tell them.
Over a 24-hour period tracking the shopping cart service, 99.94% of requests encountered exactly one version of the data.
99.94%.
Yeah.
Despite the architecture explicitly allowing data to diverge, it almost never actually does. The background anti-entropy mechanisms and the gossip protocols are so fiercely efficient that they resolve inconsistencies faster than human users can trigger them.
It really speaks to the immense speed of Amazon's internal network backbone.
But it gets better. The paper analyzes the remaining 0.06% of requests that did experience a version conflict.
Right.
The engineers found that these rare conflicts were almost never caused by hardware failures or network partitions.
No, they were caused by automated bots.
Bots.
Web scrapers and automated programs concurrently pounding the shopping cart API, writing to the same object at superhuman speeds, generating artificial collisions that a human user clicking a mouse could never achieve.
The system is so remarkably resilient that hardware failure is essentially a solved problem. The only thing breaking it is other machines moving too fast.
It's wild. Amazon also continually optimized the network hops involved in every transaction. They recognized that the routing layer was introducing unnecessary latency.
How so?
Well, initially, a client request would hit a generic load balancer, which would blindly forward the request to any random Dynamo node.
Okay.
That node would evaluate the hash, realize the data actually belonged to a different node, and forward the request again.
So extra hops. To eliminate that extra hop, they moved the routing intelligence, the state machine, directly into the client applications.
Yes. The client application periodically taps into the gossip protocol to download the current topology of the ring.
It gets the map.
Right. When a service needs to write data, it already possesses the hash map. It calculates the MD5 hash locally, identifies the precise node responsible for the data, and connects directly to it, bypassing the load balancer entirely.
And the paper notes that this client-driven coordination shaved 30 milliseconds off the 99.9th percentile latency.
Which is massive.
Yeah. In a 300 millisecond SLA window, eliminating 10% of your latency just by giving the client a map is a huge architectural victory.
But the engineers also realized they had to protect the system from itself. All of these brilliant background processes, the Merkle tree synchronization, the gossip protocol chatter, the hinted handoff deliveries, they all require CPU cycles and disk I/O.
They aren't free.
No. And during peak traffic, these background tasks were competing with live customer requests for resources.
You can't let the janitorial staff block the aisles while customers are trying to shop, so they had to implement admission control.
They built an admission controller into every single node. It constantly monitors the latency of foreground read and write operations.
The customer traffic.
Right. If it detects that the 99th percentile latency is rising dangerously close to the threshold, it forcefully throttles the background tasks.
It just pauses the cleanup.
It dynamically reduces the time slices allocated to anti-entropy until the customer-facing performance stabilizes. It operates as a self-regulating biological system, prioritizing survival, meaning customer requests over hygiene. The background sinks under stress.
This highlights the ultimate philosophy of the Dynamo architecture, doesn't it? The paper makes it explicitly clear that Dynamo is not a monolithic, one-size-fits-all database.
Far from it.
It is a highly tunable engine. It exposes the N, R, and W parameters as dials that developers can adjust based on the specific business needs of their service.
Because the architecture acknowledges that different data profiles have vastly different requirements.
Give me an example.
Well, take the shopping cart service. It prioritizes writes above all else. They might configure the system with W equals 1 or W equals 2, intentionally embracing eventual consistency to ensure the cart never stalls.
But consider a totally different service, like the product catalog. The catalog data is updated very infrequently, right?
Maybe a batch job overnight.
Yeah, but millions of customers read it every second. So for the catalog, you don't care about write availability. You care about read speed and consistency.
So a developer managing the catalog service would tune Dynamo completely differently. They might set R equals 1 to ensure lightning-fast reads from any available local node.
And set W equals N to force any rare updates to synchronously replicate to every single node before returning a success message.
Exactly. Dynamo basically provided Amazon's hundreds of autonomous engineering teams with a shared, scalable infrastructure that could morph to fit highly specific contradictory business logic.
Let's summarize the immense ground we've covered today. Amazon encountered an existential scaling crisis where traditional ACD-compliant relational databases just could not sustain the 99.9th percentile SLAs required for their new microservice architecture.
Right.
Recognizing that network partitions are a physical inevitability, they explicitly chose availability over consistency. They mandated an always writable system where a user's action is never rejected.
The shopping cart imperative.
To engineer this, they abandoned centralized control in favor of a symmetric, consistent hashing ring utilizing virtual nodes for load distribution.
And they employed vector clock to track causal histories when parallel realities inevitably formed, pushing the complex task of semantic reconciliation up to the client applications.
They instituted sloppy quorums and hinted handoffs to ensure data could be written even when primary data centers were completely dark, relying on nodes to act as temporal delivery drivers.
And they bound the entire system together with cryptographic Merkle trees and gossip protocols to silently heal the entropy in the background.
It is just a staggering achievement in distributed systems engineering that essentially laid the groundwork for the modern cloud.
The Dynamo paper transcends software engineering, really. It is a masterclass in aligning technical constraints with harsh business realities.
Yeah.
They evaluated the theoretical boundaries of computer science and navigated around them by deeply understanding their own operational priorities.
I think the underlying lesson here extends beyond database architecture, though. In complex systems, and frankly in human organizations, you simply cannot have perfect, infallible consistency and unbreakable forward momentum simultaneously.
That's a great point.
When faced with chaos, you often have to intentionally accept temporary inconsistencies. A messy desk, a misaligned team, a divergent version of a document.
Right. You prioritize the availability of progress.
Trusting that you have the mechanisms to reconcile the differences and clean up the entropy later.
It's an architecture that mirrors the realities of asynchronous human collaboration. We operate on eventual consistency every day.
Which brings me to a final thought I want to leave you with. Our global digital infrastructure, the apps we use, the financial ledgers we rely on, the social media feeds we consume, is increasingly built on these exact principles of eventual consistency rather than absolute immediate truth.
Yeah, it's true.
So how does that underlying architecture shape our human expectation of reality in the digital age? When you pull to refresh a news aggregator or check a stock ticker, are you simply looking at a divergent version of reality, waiting for a background gossip protocol to reconcile the truth?
It's something to think about.
We are living inside a massive distributed system of eventual consistency, just something to ponder the next time you click Add to Cart.